It's like just it's like a
So great, so let's get started, everyone. So today we're going to talk about gradient descent, and so we'll actually go through the algorithm today, which is actually going to be so surprisingly simple. Once we go through the algorithm, there are a couple of kind of knobs you can tune in the algorithm, and we'll talk about the choice of those knobs, right? So, and through the process, we'll talk about gradient descent, unlike an algorithm, a discrete algorithm. Sorting, right? If you sort a list and it's discrete list, it's going to give you the precise output at the end. Gradient descent is not going to work like that. It's going to kind of keep getting closer and closer to the right answer, but it's unless there's really special structure, it's not ever going to actually get there. And so we're going to see how fast it gets there, and we're going to use ideas about convexity to kind of get a sense of how fast the gradient descent algorithm actually works. So it's going to be similar in some sense to the probabilistic part of the class where we got more and more samples, we got closer and closer to the right solution. But we're not getting more samples, we're just running the algorithm longer. And then we'll see later in the semester, we'll see more algorithms kind of in this theme that are iterative like this, but aren't directly gradient descent algorithms. And then we'll see more uses of this and so forth. So the other announcement is that next Tuesday, I'm not going to be here in class. Where I have to do some duty on the research side of my job. So I won't be able to be in class. So Mesam, so as the TA is going to be giving the lecture, it's going to be the same setup I use here. Hopefully everything goes according to plan. So it'll still be on Zoom and so still recorded. I think everything will go about the same. Lecture on this same sort of material I was gonna lecture on. So I have full confidence in Miss Sam. He's he's a PhD student, so he's working with me, and he's also taught for many years before. So I think everything will go smoothly. Okay. Let's look at the schedule. So just a bit. So we're in gradient descent. I will show an example today, and Colab, that'll be very helpful for your homework 3. I basically expect you to take out the example function I have in there and replace the one in the homework, and just a few other things as what you need to do for the homework. It should be a pretty straightforward extension of forcing you to understand how the code is actually working in there. But homework 3 is coming up, due next Tuesday. Again, I'd say traditionally homework 3 and 4 are the ones that are the most time consuming for students in this course. Okay. Homework 3 has a couple of newer things you're doing in Python, a bit more than a bit larger extensions than you've done before, and similar with homework 4. So make sure to allocate a little bit more time for those than you did the first 2 homeworks. I think homework 5 should be a bit more kind of not as time consuming for most students again. So try and keep that in mind as you plan to complete homework 3. Right, and then quiz 4 will come next week, and that'll be on basically the gradient descent section of class. So, okay, great. Let's get to the lecture. Okay, but before we get into the algorithm, I just wanted to review a couple things about so gradients. Again, we're going to have a function that the function is going to have a domain of RD and a range of R, right? So this means that it goes from you can view this as the domain here. We'll use alpha in RD, and the output is so real values, right? And so this is a function. So for any value of alpha, right, it gives you a unique value in the range, the output of the function, right? So this would be f of alpha, right? Okay, and then we define the gradient of this function. Again, for it's harder to draw multi-dimensional functions. We'll plot some today, so you'll be able to get a sense of how to see them from plotting. We'll write this as nabla f. This is the gradient of f. And this is just going to be, you can just write this as the partial derivatives of f with respect to each of the coordinates of, of alpha the input. So d f d alpha 2 up to d f d alpha d. Okay. Okay, and so we talked, and these partial derivatives in general won't be hard. We'll try and design functions f. F will be the cost function that we're trying to optimize for some model, and that's what the lecture on next Tuesday will be about. And so we will design these so that the derivatives are so going to be easy. And so this is known as the gradient of f. And we had talked before about these directional derivative. Okay, this was written as nabla of u, which is some direction. Now u is going to be an element also of RD, and it's going to be it's going to be a unit vector. So the norm of it is 1. It doesn't have scale information, it's just pointing in some direction, right? And so this, if we evaluate this at alpha, this is going to be equivalent to just starting with our gradient function. Okay, so the gradient gives us the output is now a vector. Okay, and we're going to take this vector dot product with u. Okay, so once we have the gradient function, we actually get pretty easily all of the directional derivatives. We just take the direction that we want to get the derivative in, and we take the dot product with this gradient vector, and now the output of here is now is just a real value again. Remember, the output of the gradient is the d-dimensional vector, but the output of a directional derivative, I'm looking at one direction, how quickly is it increasing in that direction? This is just a scalar value again as the output, right? Or maybe this is scalar value as the output. All right, so what's interesting about this is now we can think about what happens when we change u, right? And I'd like to get this gradient, this directional derivative, as large as possible. Okay, I'd like to make this as large as possible, so it's increasing the function as fast as possible. And I can choose only, these unit vectors. Which unit vector do I choose? to make this as large as possible. Yeah. Oh, here we go.
One in the direction.
Yes. Yeah, that's exactly right. If I take u as the gradient and I normalize it, so it's a unit vector, then I look at this u f of alpha, I'm going to get back the gradient times the gradient, so normalized, and the scale of this, right? So this is basically, it's going to return a scalar, and the size of it is just going to be the norm of, so the gradient here. That's right. So normally, if I do the nabla f times nabla, dot nabla f, I get the norm squared, but I'm dividing by the norm because this is unit vector, so I just get the norm of, so nabla f, and so that's as large as it can be, right? And if I project onto, if I do a dot product with a unit vector, I'm projecting some vector, right? So I have, get to your question in a second. So I've got some direction nabla f, and I project onto a direction u, which is a unit vector. What I'm doing is I'm looking at the length after this projection, and what I'm getting is the length of it after this projection. I can make the length as long as possible. If u is exactly on this, then the projection is not shrinking anything, right? So if I orient u exactly in this direction, I get the maximum scale, and that means the maximum increase, the maximum rate of increase. Yes? Yeah, that's the norm of nabla f. Okay, this is unclear enough. I will rewrite it clearly. Hopefully, nabla f norm. Okay, great. Right, so if I choose this direction u to be aligned with nabla f, I get the full length here, right? The full length of this vector, and that means where if anything else, I'm kind of decreasing this length. Okay. Another thing is that I'm saying how much is it increasing in any direction? There's kind of some underlying function that's smooth under here, and this is kind of giving me kind of a linear approximation of this. Kind of, you can see that because I'm taking the dot products. If I do it orthogonal, the linear approximation is 0. Okay, and so I can choose. This gradient is giving me the direction of steepest increase, right? So by choosing the direction, that means the directional derivative is greatest. I'm increasing the most in the direction aligned with the gradient. So I can just use the gradient as the direction of increasing the most. Okay. And okay, so now we're going to want to, now we want to look at gradient descent. In gradient descent, we want to decrease, we want to find the minimum of a function. So now we're going to want to go in the negative direction of this. This is increasing the function, right? So if I'm right here, if this is alpha, then the gradient is pointing kind of in, think of it in this direction. So I want to go in the negative gradient, and that will go down towards a minimum. All right, so let's kind of formalize this now, talk about gradient descent as the algorithm. Okay, and so the input here is going to be a function that goes from R d to R. Okay, and I want to, and the goal, there are sometimes two ways of stating this goal. One is to find the min alpha in RD that minimizes this function, right? So I want to find this returns me the value of the minimum. You know, often we will, and it will be the same algorithm, right? We'll want to actually find the argmin of f of alpha, and this we will call alpha star, which is be the optimal choice of alpha, the one that minimizes some function. Okay. Right. So these are kind of the ways of stating the goal. We want to find the minimum of the function. And so this will be a cost function for some. It will be dependent on the data. Well, again, you'll see that on Tuesday. And then we're going to find the parameters alpha, which minimize the cost with respect to the data. Okay. And so this will be our main goal here. And so we're going to, we're going to do this when we don't have kind of a closed form way of doing this. We don't have a direct way of computing the answer, like we had in this nice case in linear regression. We had it with computing the mean and single one point. We generally won't have a general closed form for optimizing this. There'll be some special cases when we partially can do that, but in general we don't. And we'll use this gradient descent, which is a more flexible mechanism. Okay, and so the algorithm is going to be kind of fairly simple. Okay, the first step is to initialize. So I'm going to make some guess. I'm going to call this alpha superscript of 0. I'm putting the superscript inside of a parentheses to let you know that it's not going to be, I'm not taking it to some power, okay? Alpha is multidimensional vector, right? So a subscript would probably represent one of the coordinates, so that's why I'm using a superscript. And we're gonna run a bunch of steps, and the superscript will tell me what step I'm currently on, okay? Okay, and so this will be some starting position. And this is kind of a guess. If you don't know anything about the guess, probably use just all zeros. Okay, there are certain advantages to using the all zeros. If you're starting with all zeros, you're probably starting with a very simple solution. And it's probably isn't arbitrarily far from the right solution. So that's probably a good initial guess if you don't know anything else. Okay, and this is an element of RD. And then we're going to set some parameter k equals to 0. So the superscript will be k. K will be the number of steps I've taken so far. At the start, I've taken 0 steps. Okay. Okay. And then the algorithm is going to be a simple. So it's going to be a simple loop. We're going to do repeat the following procedure. Alpha k plus 1. So this will be our estimation of the parameters, right, that we're trying to update. And so this was going to we're going to start with the old guess, that's alpha k, right? And we're going to subtract gamma k times the gradient f at alpha k. Okay, so at the old guess. Okay, and we're going to, on the side, we're going to do k gets k plus 1. Okay, so we're going to increment our counter, right? If you have a for loop, then that handles the increments for you and so forth. But okay, so this is basically the algorithm. All right, let me just put a highlight on this. Super important to understand what this is. We will talk about the pieces in a second. And question.
So I want to go forward.
Yeah. Right. So okay. So there are a couple of wrapper things. Let me just say some wrapper parts. So there's until. Okay. And so there are two conditions, two ways you can think of the end condition of this, right? How many steps we do, either until k equals some t, right? You set some upper bound on the number of steps, or what's kind of more formal, like in practice, you'd probably just set, I'm going to do 20 steps or 100 steps, you know, and maybe you play around with that. But kind of if you want to think kind of a more, formal way of thinking about what is the right thing to do, you would typically write a condition, alpha k, let's say alpha k. If I look at the gradient at alpha k, right, which I had computed above here, right? So if I look at the norm of the gradient at alpha k, and this is less than some sort of threshold until this, and then I stop, and then I return alpha k. Okay, so these are two kind of conditions. Either I'm going to run 20 steps, or I'm going to run for 100 steps. You might do something where you plot some stuff. We'll talk about that probably. You'll do something like that in your homework, or you might look at this condition. If the gradient is sufficiently small, then that's probably a good way to check whether I want to stop, by looking at how small the gradient is. Yes?
To be clear, those two t's are different, right?
Yeah, this is supposed to be tau, and this is an uppercase T. Yeah, so those are not this. You wouldn't do both of these. I would probably do one of these two things. You could put both conditions. Yeah, but I mean, there's some sort of threshold, either in the number of steps or the gradient becomes small enough. Yeah. Yeah, great. Good question. This is called, the learning rate. And in most cases, gamma is going to be, usually you're going to have this as going to be fixed, just a fixed value. It could be 1. Okay, if you don't know anything about it, you might just put a 1 there. Okay, and just leave it fixed. We will talk about the meaning and how to choose the learning rate and the importance of choosing the learning rate in the convergence. But it's going to be some quantity that scales the gradient. How big of a step? So the larger that is, you take a bigger step. The smaller it is, you take a smaller step. Yeah. Yeah, so all these, this is, it's not to the power, it's just a superscript and indicator. This is k plus 1. This is k. This is k, right? This is k again, right? So I'm just saying, there's probably, typically when you would write this, I'm trying to be a little bit more explicit so it's clear that, you could even drop the superscripts and you can just overwrite the alpha parameters, right? So it might be simpler to just write here. So I can just say alpha start, repeat alpha get alpha plus the gradient at alpha, or sorry, it should be subtracting times the learning rate. A common mistake is to write plus instead of minus. Say until say the okay, and then return alpha. Okay, so you could write it this way. It's harder to write how many steps I took because I'm no longer keeping track of the number of steps here, right? But I can just overwrite the parameters I have every step. This is more space efficient. We will, in the code, we'll do something closer to this because I'm going to draw a picture, and I'm going to draw every state as we go, and you'll be able to trace it out. And then you have the kth plus 1 state and so forth. Okay, so is that clear? Okay. Right, so it's a pretty simple algorithm. I'm making a guess on the state. I'm taking the gradient that tells me the direction of largest increase. I'm going in the negative direction of it, so it's decreasing the function in that direction by the learning rate. The learning rate is how quickly I move. And I just do this until I get close to the solution. How do I know if I'm close to the solution? Well, if I took a lot of steps, I'm hopefully close. Or if the gradient is small, then I'm hopefully close. Okay. Something to keep in mind is that we talked about normalizing the gradient to think about the direction of maximal, so directional derivative. The gradient itself captures scale information. This is a vector. The gradient is a d-dimensional vector. It's not a unit vector. When the gradient is larger, I'm already taking larger steps. So typically, if you're further away from the solution, you'll be automatically taking larger steps, even if the learning rate is constant. Okay, it automatically builds that in as you get closer to the solution, right? If you remember kind of from calculus, right? If I have a function, right? If this is my function f, and if I'm up here, the gradient might be large, but if I'm, say, here, let's say this is alpha 0, and this is alpha 2, after 2 more steps, the gradient at this point, actually alphas are down here, but the gradient at this point here is going to be more flat, right? Think of it's pointing in a direction, but the magnitude of it tells you how quickly the function is decreasing. And as it flattens out towards the bottom, the gradient gets closer to 0. The minimum has a property that the gradient is exactly 0 at the minimum. So as I get closer and closer to it, the gradient is getting closer and closer to 0, and the step size is getting smaller. That's automatically happening. And that's why when the gradient gets small, I'm probably close to, the minimum. And if it's convex, then I can actually argue I am close to the minimum. Yeah.
So does this work with shape classes?
Yeah, so if it's not a convex function, right, is maybe what you're thinking. If it's a convex function, it will look kind of like a parabola. Think of a convex function as kind of like a parabola, but higher dimensional, hopefully, and that's how we will design our functions. If it is not like that, it's like the function I drew here, where it has multiple local minimum. Well, yeah, so it could get stuck over on the left side there, where I drew this red alpha point, right? That's not the true global minimum, and it might not find the true global minimum. It will stop when it gets there. It can stop at a local minimum. At a convex function, there are no local minimums that are not also so global minimums. There are no saddle points. So it can't get stuck any place like that. So we can guarantee, and what I'm going to talk about next is how we can get guarantees under if our function is going to be so convex, and even stronger guarantees if it's strongly convex. Yeah.
What if it's convex, but like the gradient increases as you get closer to the zero point?
Well, it can't do that if it's convex, actually. So what's an easy way to explain this? I can. So if it's yeah, okay. So, it mostly can't do that. There's a weird things in higher dimensions where on one side of the minimum, it can be going really slowly, and the other side very quickly, and this leads to some chaos that can happen, right? But let's So the weirdest situation you could think of is if the function looks like this, and then it jumps up here. Okay, so if this is alpha star, right? This is the minimum point here. Okay, what's going on here, and this I think is useful to draw. If I drew let me draw as a function of alpha. So in general, alpha here is in RD, but we can only draw one dimension. This will be the magnitude of f of alpha. Okay? So not looking at the direction will always point going up, so kind of away from the minimum. Okay, but the gradient is kind of the slope. In one dimension, it's the derivative, it's the slope of here, and the slope is very small as it gets close, right? So that means that the gradient is going to be small here and increasing, right? And the gradient is increasing along with this function here. But what's happening here is that the gradient also, it immediately jumps up. Okay, so it's constant. The gradient is constant along here. It doesn't change, but it's large. Okay, and so what could happen is you could have if this is a convex function, a not very nice one, right? We don't want non-nice ones. It's not strongly convex, but it's convex. So we could be walking along, then immediately jump over here, and then it's going to go back this way, but it's going to do a big jump. This would be kind of problematic. If instead, I think what you maybe have in mind is instead a function that looks like this, and then the gradient increases like this. So like here, the gradient is larger, closer to alpha 0 here, right? Right, this is alpha 0, and the gradient is larger here than it is here. The gradient's very small here, and then it gets close to the minimum as it's larger. Why, if I have convex functions, is this not a concern? Yep. Yeah, right. This function is not so convex. Remember, if I have P and Q, right, and I draw the line between here, the convex functions, the blue function always needs to stay below this line, but in this case, when I have this event like this, the function is above this line.
It's just the two straight lines. You don't have the.
Yeah, okay, then it's not getting smaller as it gets closer, right? And so it's not getting bigger either, but it's not getting smaller, right? That actually does arise. That would be like, that's kind of like an L1 cost. If I looked at the sum of the errors, the absolute values of errors, instead of the sum of the squared errors, I get functions that look just like this. Now, if you average over a bunch of these, it turns out it smooths out, but not entirely, right? So I get a lot less information with those functions. And so that's one reason why we typically don't use them, even though maybe it's a little bit more natural. But the squared errors gives you these parabolic functions, and as I'll discuss next, those actually we can guarantee that gradient descent will work faster on those, because the gradient, essentially because the gradient does get, it is going to get smaller as we get closer to the minimum. Okay, and that's the power of these convex functions. Great. These are great questions. Okay. Okay, great. So let's talk about so if you go back to here, there were kind of two important questions to kind of ask, but we've kind of previewed both of them already. One is the stopping condition, right? The gradient will get smaller as we get closer to tau. So that tells us, okay, we're close to the minimum, assuming the function is convex, if the gradient is small. Okay, so that the norm of the gradient is small, or we've had some number of steps. This is easier to do. But we have computed this gradient, so we just have to compute its norm. So it's not that much extra work. Oh, the other thing to point out is we never computed the function value. We don't need to be able to compute the function value. We only need to be able to compute the gradient. The function value does not show up in this algorithm. It's kind of a neat observation. I don't need to be able to compute the function. I just need to be able to compute its gradient. Okay, the learning rate is the other thing, right? I said if you don't know anything, leave it kind of constant. Maybe 1 is probably okay. What can we say about the, about the choice of the learning rate? Okay, and it will, in most of what we'll talk about, it will be a constant value. But towards the end of this lecture, we will say, okay, what if we were to adjust it as we go? As we know something about the system, we can kind of learn the learning rate, and I'll mention that at the end of this lecture. Okay, but okay, so how do we choose this learning rate? Before we do that, I need to tell you, if we were to choose the learning rate in a way which is correct, we're going to get some sort of guarantees on how well we do if the function is also going to be so convex. Okay. Okay, and we need to define a couple of things about functions in order to understand this. So first, I'm going to start with a function. I'm going to state this generally from RD to RK, function G. Okay, in general, it'll be K will be equal to D here. Okay, but it could be any things, and I'm going to say that this function is L, so Lipschitz. Okay, if for all P and Q in RD, I'm going to have the following property, that G of P, if I look at the function values of G of Q, right, and I say these are going to be close, the values are going to be close if the distance between P and Q is close, and it'll be controlled by this parameter L. Okay, so if the smaller L is, the closer they are. So if P and Q are close to each other, then the function values are close, right? So if I have a continuous function, right, if this is G here, then it means if the slope is bounded, if the slope is bounded, then the output of the function, so might just be one-dimensional, right? Then the Lipschitz rate of L is bounded by the slope, the maximum slope, right? So the maximum slope might be occurring here. If this has a slope of L, then that tells me how quickly it's changing. So if something has always bounded slope, or the norm of the, it's not changing too quickly, then it's L Lipschitz. This is kind of a nicer function. Okay, and I didn't use F here because I normally want to apply this on the gradient, right? The gradient goes from RD to RD. Okay, so if I can say if G equals the gradient of F is L so Lipschitz, okay, and we set gamma to be less than or equal to 1 over L, okay? So if it's L is small, the slope is small, then we can set, then 1 over L is large, and we can set the learning rate to be larger. We can take larger steps, right? So if I have this property, then then gradient descent on F will converge to a stationary point. Okay, a stationary point would be probably like a local minimum. It could get stuck at a local maximum or a saddle point, one of these other weird points. But if it's convex, I know I don't have any of those. Okay, so if I have a convex function, then it will converge to the global, so minimum. So then if F is convex, then I can say gradient descent will go to the global min, right? The stationary point, the only one is the global min. And in fact, I can say that if I run for k equals some constant over epsilon steps, then I will have that f of alpha k minus f of alpha star, where alpha star is the optimal, will be less than epsilon. Okay, epsilon is going to be some sort of kind of error tolerance I have. And so if I want to get to a smaller error tolerance, that means closer to the optimal solution, the steps I have will always be larger than the optimal solution, because the optimal is the minimum. So always be larger, but it won't be too much larger. And the number of steps is roughly 1 over epsilon, right? So if epsilon is small, then I need more steps. Okay, so it tells me how fast it's guaranteed to converge. If I have convexity and I set the learning rate so it's not too big compared to the Lipschitz factor, right? Remember, if I have this case and where the Lipschitz factor on the gradient can change really quickly, I might get something kind of haywire going. This gradient is not Lipschitz. It can change really quickly. There's a jump in the gradient function here, so this is not Lipschitz. But if I have kind of a smooth function, then it's going to be Lipschitz, and then I'm going to get convergence. And if I have a convex function that has a smooth gradient, the gradient changes in a bounded way, then I can guarantee I'm going to converge to the global minimum and in this number of steps. Okay, so this is pretty cool. I just need convexity to get this. If I have a convex function and it doesn't have jumps in the gradient descent will work. Okay. Yeah.
And the k equals c over c.
Yeah, okay, so C, so that's a great question. So this C, what is this constant parameter, right? This is some constant. And this is hard to know what the constant is, okay? It depends partially on where you initialize. If I start further away from the right solution, it will take more steps. If the Lipschitz factor is larger, so the learning rate has to be smaller, it will take more steps. So it somehow depends on my initial conditions and on the learning rate and some other things, but those are kind of controlled. They're controlled in that way. I want to know how the error decreases as I take steps. And that's what this is telling me. The gradient descent typically looks at the rate of convergence, but you can write it in terms of the number of steps. This is what computer scientists are probably a little bit more used to. Then this is the right way to think about it. Okay. Yeah. Yes, f of alpha k minus f of alpha star. This is where you are after k steps. After k steps, and this is the optimal. Okay, and I want to see how close am I to the optimal on the function. Okay, is this a good result, right? If I want to get to within a factor of, or a distance of say 0.01 from the true optimal, I need on the order of like 100 steps. Think of it as O of 1 over epsilon. Is that can be a, so a good result? It seems pretty good. Remember, in the sampling, the central limit theorem, we used the Chernoff-Hofting bound. We needed roughly 1 over epsilon squared samples to get within epsilon error. Now we need 1 over epsilon. This is better than that. However, from gradient descent perspective, this is not a very good result. A lot of times, we can do significantly better than this, exponentially better than this rate. Okay, so we're going to do, exponentially better. That means we can get something like log of 1 over epsilon steps. Okay, so let me tell you that result next. Okay, and then I'll try and draw a picture to conceptualize how to put these things together. For this, we need strongly convex so functions. Okay, strongly. Okay. So those are some strong functions you have there. You've been watching House of the Dragon. All right. Not meant as offense to those functions. They're actually strongly convex. So, okay. All right. Okay. So we're gonna say this is an eta strongly convex. So we're going to quantify how strong this is in so that's an eta. In LaTeX, it's a Greek letter, typically what is used here. And we're going to assume that eta is greater than 0, strictly greater than 0. And this will be true if for all alpha and p in RD. We're going to have the following, that f of p is going to be greater than f of alpha. Okay, remember alpha is where we are, and we want to consider any other p on this function. So I'll draw a little bit better picture now, but just to help guide you a little bit. We're going to have, this is our function. We're going to have a point P, and we had alpha, right? And so we're going to compare the values at alpha and P, okay? And we want it to be greater than alpha. There's more to this equation, okay? Plus the gradient at alpha dotted with P minus alpha. Okay, so what this is doing, okay, the dotting with P minus alpha is basically reducing it to a one-dimensional problem, right? This d-dimensional function we need to be concerned with, but we're dotting with a vector in the plane that has P and alpha in it, right? So the x-axis in that picture is d-dimensional, but we're taking a dot product, we're taking essentially the directional derivative in the direction of P alpha. There's some scale in there as well, so it's not exactly the directional derivative, but we're restricting to the direction that has P and alpha in it, and we're looking at the gradient in that direction, okay? And this holds for all alpha and P, and there's another term, eta has to show up here, and eta divided by 2 plus P minus alpha squared. Okay, so what is that doing there? Okay. Okay, so that is a squared term. The first one, okay, F alpha is the derivative the function value at alpha, the gradient at f alpha is like a linear approximation. And I'm restricting it to the direction between p and alpha. And then I'm looking at a squared approximation, and the eta is on the squared term there. Okay, and I'm saying it's the function value of p is greater than this. Okay, so what is going on here? Let me draw a little bit bigger function here. Okay, so we're going to have, it's going to be like a parabola. This is going to be our function f. And we're going to have 2 points, alpha and p. Okay, and so we're going to look at, let's see, we have this point right here. This is f of alpha. This point here is f of p. Okay, now we're going to approximate this in a few ways. We're going to draw the gradient, and so this is d dimensions, but by we're restricting in the 1-dimension subspace that contains p and alpha. Okay, and then the gradient is basically telling me, okay, what is the a linear approximation here, right? It's telling me the slope. It's telling me what is the slope at alpha, right? This is the gradient at alpha, and the slope, so that gives me, I'm adding a linear approximation. So as I move away from alpha in the direction of p, this is the linear approximation to the blue function f at alpha. Okay, and I'm saying what is, if I use this linear approximation, f of p, the approximation would be right down here, basically at the origin, right where I drew this point. That's where it crosses over this value p here. But then I'm adding a third term, and this is a squared term. So that's a kind of so some sort of parabola, and I'm getting a quadratic approximation now. So now I have another function coming in here, and hopefully I can draw this. And so the blue function should always be larger, right? If it's convex, the convex property I have is the blue function f is always larger than the linear approximation. The line must always stay below the function. That's convexity gives me that already. Okay, but now I'm saying there's also a quadratic function that's also smaller than f. Okay, right? So it's another parabola. This orange one is another parabola here, and this is starting with the linear approximation, and it's adding a term which is going to be quadratic here. Okay, and this also stays below. When I can do this for every alpha and p, that's when it's going to be so strongly convex. Okay. Okay, there's another picture you can actually draw here that's also interesting. I'm going to also consider another function that's another parabola. Okay, this function here, this would be f alpha plus f alpha, the gradient at f alpha p minus alpha plus L over 2 p minus alpha squared. This is another parabola. It's another quadratic function that is, but that's always above. That's always above the function f. And notice I used L here. This function, if this function is always less than f at p, then it implies f is that the gradient of f is L So Lipschitz. Okay. So that means that the gradient does not change too fast. If I can always, for some fixed L, I can always fit a parabola that looks like this everywhere. I can shift it. It's a different parabola, kind of it touches it in a slightly different way, different places, but it's always above. That means that the gradient is L Lipschitz. Go back to this example here, right? I couldn't squeeze it in here. That's why the gradient is not L Lipschitz. I could not fit a parabola in the slow corner. Okay, so this means it's L Lipschitz. This was the condition I needed for the first statement about the convergence. For if I have a strongly convex function and eta strongly convex function, I can now say something stronger here. Okay, so if f r d to r is eta strongly convex and nabla f, the gradient of f is L, so Lipschitz, and I set the learning rate is going to be less than 2 divided by L plus eta. Okay. Okay, then after k equals some constant times the log of 1 over epsilon steps, then I'm going to have that f of alpha k is going to minus f of alpha star is going to be less than epsilon. Okay. So if I have strongly convex function and I set the learning rate, basically you want to set it as roughly at 2 over like the average. You know, you have these two parabolic functions, and I know the blue one is sandwiched in between them, and I can set it as kind of the average of these two bounds I have. Then I will get some learning rate, which has a pattern like this. Yeah. No, for that one, I want f of p to be so greater or equal to the orange function and less than or equal to the purple function, right? So I could write these all in one line where the purple function is on the left, and that's less than or equal to p, f of p, and that's less than or equal to the black function, which I drew here in orange. All right, yeah, this corresponds with the orange function here. Good. So I want them, the blue one, the true function is sandwiched in between. Okay, if I know it's kind of defined by these parabolic functions, these squared error functions, then it will have to have some form like this, right? Yeah.
So the purple one, do you have f of p is greater than both of those functions? I think.
F of p should be less than, so the f of p should be less than the purple function. Let me write this in blue here. This is f of p. Right, so f of p is less than the purple function. Oh, no, I wrote it as greater. Okay, good. So it should be, that function should be greater than f of p. Okay, good. Thank you also. Yeah, great. Okay, good. Okay, Okay, right. Okay, so I get this learning rate. This is called, so linear, so convergence, okay? So this is linear convergence. It's got the other ones seem like linear convergence. It's going down at a linear rate, but the log is going down. The log of the difference is going down at a linear rate here. They typically plot it on a log scale, and on a log scale, the error goes down at a rate that looks so linear. That's where linear convergence come from. There's a quadratic convergence where on the log scale, it goes down quadratically. Okay, but this is linear convergence. This is much, much better, exponentially better. What is this saying? This is, it says, the way to interpret this is basically every constant number of steps I take, I resolve one digit of precision, right? I'm getting the right function value, and the function value is getting a digit of precision every constant number of steps. That's pretty cool, right? So take 2 steps, you resolve the first digit of precision. There's 2 more steps, you get the second digit of precision. Okay, and it gets harder and harder as you go, but it's still getting a new digit of precision every constant number of steps. So this is a really fast convergence rate, and this is what we like to see. That means like if you set this up in 10 or 20 steps, you should get pretty as close to the optimal as you can hope for. As we'll see, this F is derived from data. And we already had the sample complexity on the data that we needed a lot of data points to really trust the value, to trust the cost function that we're doing. And so we don't trust the cost function more than so many digits of precision, and we can reach that with a very small number of steps. Okay, so this might as well be converging, again, the right solution after 10 steps. So that's really quick. Yeah.
So can we say a function is Lipschitz if it is differentiable everywhere? Like it doesn't have an infinite derivative?
Yes, it will be L Lipschitz for some L if it's okay, I take that back. If I look at the function x squared, it has a derivative everywhere, but as I get further away from 0, the derivative goes to infinity. So it's not L Lipschitz everywhere, right? So the quadratic function is not L Lipschitz, even though the derivative is defined everywhere. But we care about L Lipschitz of the gradient, right? So we're really thinking, when we think about the L Lipschitz, we're really thinking about this, the second order term, the coefficient on the second order term. So we need so it's still okay, right? So quadratic functions are still okay. If I take a derivative of a quadratic function, I get a linear function typically, right? And the linear functions, they have their L Lipschitz, it's usually a constant. Okay. Yeah.
If you're talking about like f is x squared, then the derivative of f would be x, and that still goes to infinity. Is that L Lipschitz?
But the rate of change is constant, right? So I say if I move a distance of 1, then the function value should move a distance of at most L. If I move a distance of 2, it moves at most 2L, right? So that's consistent with the linear function.
So if it's like, if f is x cubed, would that still work?
Yeah, that would be a problem, right? Then the gradient would not have a bounded Lipschitz factor, right? And then I can't apply this result. All right, so I really like these squared error functions. They're really nice. This is one of the reasons squared error functions are super nice here. Okay. I was hoping we were a little bit past midway and I could give you guys a break, but I wanted to we have 15 minutes left, so some stuff I want to get through here. A lot of great questions though. So I want to do two more things in this lecture. One is tell you about some ways to adjust the learning rate automatically, and one is show you a demo. Let me start with the demo, and then we'll come back to the adjustable, adjusting the learning rate. Okay. Great. Okay, so yeah, because you're going to want to use this in your homework. Okay, so we're going to run gradient descent. We're going to use Python, NumPy. We're going to plot stuff, so matplotlib here. Okay, we're going to start with a two-dimensional function. For this homework, we're going to worry about two-dimensional functions. We'll be able to, I drew one-dimensional functions on the slide. With the Python, I can draw two-dimensional functions, as we'll see. Right, so I'm going to define a function here. Okay, and it's just the same equation I wrote up there as x and y. And then I want to encode the gradient of the function. Okay, and so this is the gradient of this function. It's the two, basically it's the two partial derivatives, df dx and df dy, right? These are the two kind of things I need, and so it returns an array. It returns a two-dimensional function. Okay. Okay, and now I'm going to draw a contour plot, which we'll show below. These things in the homework, you might need to adjust these, especially on the function F2, the second more trickier function. So this is drawing between 0 and 5 by 0 and 5 and 26 kind of grid cells effectively in each dimension. And we'll create this thing called a mesh grid. This is kind of like this lin space I use for plotting, but now it gives me a grid. And it'll compute the function on all these values. And then it can basically, it's going to, and there's this lin space thing that will give me the these different, I'll draw 20 different levels. So I'm going to draw the levels where the function value is the same on those levels, and each level will have a different color, and you'll be able to see kind of the shape of the function here. Okay, we'll initialize it at 5, 4, and we'll do 10 iterations here. And I'm going to store stuff in an array, the output in an array. Every step, I'm going to load it into the next element in this array, because then we'll be able to draw a picture, set the learning rate gamma equals 0.5, okay? And then here's the actual algorithm, the gradient descent algorithm, right? It's just this iteration. I have V is my alpha in this case, right? And I update by minus the learning rate times the gradient. That's it, okay? And I'm storing it in there. And then, okay, here's the fun part. I get to plot this contour plot. Okay, so how to read this, right? The X and the Y axis, this is the domain of my function, right? And I'm plotting a bunch of points that have the same value, the same function value, right? They get the same color, and they go from small values more purple to high values more yellow. So it's higher up in this corner. And I've started here, and I see I draw every step in red line, and the blue points are the steps along here. Okay, and I can see after the final gradient gets smaller. The gradient, oftentimes you might not be able to plot a two-dimensional function like this, but you can plot the gradient, and the gradient should be decreasing, and that's a good indication of how well you are to converging. If the gradient is not always decreasing, probably something kind of funny is happening. Okay, and so let's go and actually play with the learning rate here. And I think it's important to see what happens when I change this learning rate. Let's change it so it's larger. Okay, so let's,
You put a green line on accident.
oh, okay, yeah. Great. Okay, change the learning rate to, okay, rerun this and redo the contour plot. Oh, what has happened here? That is not good. Okay, I've only plotted the function in 0, 5, but my stuff jumped all over the place here. Okay, let's try something more manageable. So this learning rate is too large, if that was not clear. Okay, okay, let's try a little bit smaller. Okay, that's still too large, right? I started over here, I jumped over here, I jumped all the way up there, then I'm jumping back and forth over this minimum. Okay, my learning rate of 1 is too large in this case, okay? Okay, so let's 0.8. And well, okay, it's now I'm actually converging to the right solution here. Okay, but this is not what it's supposed to be doing. You should not be jumping back and forth across the minimum, right? I still need to get the learning rate down. We did 0.5 converge. Let's try 0.4. Okay, and okay, this is looking a little bit better, right? See how it's kind of more smoothly curving in here? This is kind of like what you want to see. Let's see, I think 0.3 is going to kind of be a sweet spot here. Okay, and 0.3 is kind of curving in. This is probably about what you'd like to see. Yeah, question?
Whenever you're like talking about the jumping, is it essentially going from right to left?
You can kind of see it by tracing out the curve, but it's basically I was going from one side of the minimum to the other, and it's I was taking too big of a step every time. Yeah.
For a, I guess a convex function, wouldn't it be possible to like take two points that are like pretty far apart, and then there's maybe a spot where the rate, just like the rate of descent would be on the path where, like in between that, it would go straight in the middle of the minimum.
Yeah, and that's pretty much what was happening there, right? It was kind of lining itself up the right to go at the minimum. Eventually, it gets. Yeah, there's a bunch of stuff in optimization theory where you would see this. It kind of is trying to line itself up at the direction of steepest descent, and then it will jump straight towards the minimum, but it overshot. And so this is 0.1. It's not quite getting there. It's too small, right?
That's a more general question. I believe gradients are never technically touches the minimum, but it pushes that in positive.
In general, it will never get to the minimum. In some cases, you know, if the function is very nice, it might hit there exactly. Or if you, but you don't expect it to ever get to the minimum. Side point: you shouldn't trust your function that much in these settings. The function is a representation of the data, and the data is a sample of reality. So it doesn't get to the minimum, but that's usually you stop before it gets to the minimum.
It's never like a relatively simple formula like this. You just take like tangent planes and find the minimum.
Yeah. Yep. In general, your functions, the next lecture, you'll see how these functions are kind of constructed from data. And as it turns out, like with tangent planes, which is, if you remember how we drive the linear regression solution, you're basically, you know, calculating the derivative exactly for all the data, and then you're solving for when that equals to 0 algebraically, and that gives you the solution. In that case, you can magically do this. In general, if you tweak it a little bit, you add a regularization term that's not the ridge term, then you can't necessarily do that anymore. And so then if you get to like deep nets or something where they're even more complicated, you're happy you can calculate the derivative, and then you can do that, and that's all you do. Okay, yeah. So in special cases, you're right, you can do this, but in general, you can't. And so you want to be able to design functions from data that has a lot of nice sort of properties here. Yeah.
Is there a way to tell, it's like looking at a function, whether or not it's convex without like applying it, like observing?
Yeah, so it's a great question. By just looking at the function. So if you just have like the equation of the function, you can calculate its second derivative, and if second derivative is always positive, then it's going to be convex. Okay. In general, we will guarantee convexity by construction. Okay, we will construct the functions from data. We'll know that each piece of it is convex, and we'll add together these pieces. And the sum of convex functions maintains convexity. Right? So if we have two convex functions, we add them together, we average them together, they're still going to be convex. And so that's how we will guarantee it. And we'll see one example on Tuesday, and then we'll see a little more in the classification section, more exotic, slightly more exotic things. Yeah.
I thought I saw somewhere that gradient descent can be applied to non-strictly convex.
Yep. It typically does pretty well. So the first result was just functions that were Lipschitz, and it will converge to a stable point, right? If it's convex, not strongly convex, but just convex, and Lipschitz, it will converge to the global minimum. In practice, in deep learning, the functions are not convex, and people run gradient descent, and it usually works. Not always, right? Sometimes it does not work, and there are lots of nuances in there about why it doesn't work. Sometimes it's because the functions are not so convex. There's another theory. There's another kind of school of thought on this, related to this over-parameterized setting. In the over-parameterized setting, you should be able to find a function that interpolates the data. That means the minimum has a function value of 0. When the minimum is a function value of 0, you can get something where if the norm of the gradient is sufficiently smaller than the distance to 0, or is larger than the distance to 0, so as you approach 0, or as the distance to optimum, and you can bound these things, then you can also show convergence without going through convexity at all. And this happens in over-parameterized settings, and this is kind of another explanation for why this might work. That's as much as I'm going to say about it, I think. But there are other schools of thought. This is the kind of the most foundational stuff that machine learning was all built on for many years, and until recently, people are only recently starting to get away from this. I still think it's really useful too. Okay. I don't think we have time to do the adjustable rate stuff. I'm gonna ask May-sam on Tuesday is probably not gonna cover this primarily. It may be interesting to look at for the part on function F2. If you don't use it, you can get full credit. I will try and find another part in the semester to fit it in. It's not too hard, and you can look at it in the book and the notes to cover it. But you can either automatically tune the learning rate by looking at how you compare to those parabolic approximations. If those seem to be aligning with what you're doing, then you keep it. But if they're misaligning, you adjust the learning rate. Or you can kind of just try and solve for it kind of empirically every step. Every step, you try a bunch of learning rates and you do something like binary search. Like binary search to try and find the best learning rate on that step. Those are kind of the two main ways that people approach this. Well, the main way they do is they just try a bunch of learning rates, just like I did, and they see which one works. That's actually probably the most common thing. You just try a bunch of learning rates, whichever one gives you the best final value at the end, that's the one you use. But there are other slightly more formal ways in the book. So, all right, well, so we'll stop there, and I will see you guys later.